Hello students, today I am going to deliver a lecture on Introduction to Analysis of Variance and One-Way Classification of Analysis of Variance. It is a brief introduction of ANOVA designed for the BSc CBCS 4th semester statistics honors students studying at colleges under Dibrugarh University. Analysis of variance is a collection of statistical models used to analyze the differences or variations among and between groups developed by statistician and evolutionary biologist Ronald Fisher. In the ANOVA setting, the observed variance in a particular variable is partitioned into components attributable to different sources of variation. ANOVA is used in the analysis of comparative experiments, those in which only the difference in outcome is of interest. The statistical significance of the experiment is determined by ratio of two variances. The basic purpose of the analysis of variance is to test the homogeneity of several means. Variation is inherent in nature. The total variation in any set of numerical data is due to a number of causes which may be classified as assignable causes and sans causes. The variation due to assignable causes can be detected and measured, whereas the variation due to sans causes is beyond the control of human hand and cannot be traced separately. The ANOVA consists in the estimation of the amount of variation due to each of the independent factors separately and then comparing these estimates due to assignable factors with the estimate due to sans factors, and the latter being known as the experimental error or simply error. The linear model of ANOVA. Let y1, y2, yn be n observable quantities, and in all cases we assume the observed value to be composed of two parts. Yi is equal to mu y plus ei. Here mu y is the true value and ei is the error. The true value mu y is the part which is due to assignable causes, and the portion that remains is the error which is due to various sans causes. The true value mu y is again assumed to be a linear function of k unknown quantities, tau 1, tau 2, tau k. They are called as effects. Thus, mu y is equal to ai1 tau 1 plus ai2 tau 2 plus plus aik tau k. They are linearly related, where aij, I takes the values 1 to 3 up to n and j takes the values 1 to 3 up to k are known, and which being usually taken to be 0 or 1. This setup, which is fundamental to analysis of variance, is called the linear model. It is possible that there may be association between errors of successive measurements, but it is assumed that the errors ei are always independent random variables. These are also assumed to have zero expectation. That means expectation of ei is equal to 0 and to be homoscedastic, that is equal variance. That is variance of ei is equal to sigma e square, say, and consequently variance of yi is equal to sigma square, and expectation of yi is equal to ai1 tau 1 plus ai2 tau 2 plus plus aik tau k, where I takes the values 1 to 3 up to n. Now, ANOVA for one-way classified data. Let us suppose that capital N observations yij, where I takes the values 1 to 3 up to k, j takes the values 1 to 3 up to ni of a random variable capital Y, are grouped on say some basis of k classes of sizes n1, n2 up to nk respectively, where capital N is equal to summation ni, I from 1 to k, is as exhibited in the following table. Here there are k classes, class 1, class 2 up to class k. This is the general class, I class, and in each class there are observations. In the first class, there are y11, y12 up to y1, n1 are the n1 observations. In the second class, there are n2 observations, y21, y22 up to y2 and n2. And for ith class, it is yi1, yi2, yini. Observations are there. So, the total of the first class is T1 dot. That is y11 plus y12 plus plus y1n1 is equal to T1 dot. Similarly, for second class, it is T2 dot. For ith class, the total is Ti dot. And for the kth class, it is Tk dot. And the mean of each class is, for the first class, it is y1 dot bar, and it is obtained by dividing T1 dot by N1, that is the total number of observation in the first class. In the second class, number of observation is N2. So T2 dot is divided by N2 and we get the mean of the second class Y2 dot bar. Similarly, Yi dot bar dot Yk dot bar. The total variation in the observation Yij can be split into the following two components. The variation between the classes or the variation due to different bases of classification, commonly known as treatments. The variation within the classes, that is the inherent variation of the random variable within the observation of a class. The first type of variation is due to assignable causes and which can be detected and controlled by human endeavor. The second type of variation is due to such causes which are beyond the control of human hand. So the main objective of ANOVA technique is to examine if there is a significant difference between the class means in view of the inherent variability within the separate classes. So let us consider the effect of k different treatments on the yield of n observations divided into k classes of sizes n1, n2 up to nk. And here the sources of variation are effect of the treatments. There are k treatments. So their effects are denoted as Ti. I takes the values 1, 2, 3 up to k, and error epsilon provided by numerous causes of such magnitude that they are not detected and identified with the knowledge that we have, and they together produce a variation of random nature obeying Gaussian law of errors. Now, mathematical model for one-way classified data. In this case, the linear mathematical model will be Yij is equal to mu I plus epsilon ij. Again, it can be arranged like this: mu plus mu I minus mu plus epsilon ij. So here it is equal to mu plus alpha I plus epsilon ij, where I is takes the values 1, 2, 3 up to k, j takes the values 1, 2, 3 up to ni. Here Yij is the yield from the jth observation taken ith treatment, and mu is the general mean effect given by mu equal to summation I from 1 to k ni mu I by capital N. Here mu I is the fixed effect due to ith treatment. And that is, if there was no treatment differences and no such causes, then the yield of each observation will be mu. Then alpha is the effect of the ith treatment given by alpha is equal to mu I minus mu. I takes the values 1, 2, 3 up to k. That is, ith treatment increases or decreases the yield by an amount of alpha I. Thus, we have summation ni alpha I from 1 to k is equal to summation I from 1 to k ni. And by putting the values of alpha I here, mu I minus mu, which is equal to summation ni mu I minus mu summation ni. So ultimately we have n mu I minus mu n, which is equal to 0. Then the fourth condition is that epsilon ij is the error effect due to suns. Now fixed effect model. Let the k levels of the factor or treatments considered are the only level of interest. All these are included in the experiment. In such cases, alpha i's are fixed unknown constants. Then the model Yij equal to mu plus alpha I plus epsilon ij is known as the fixed effect model. In this model, one would like to estimate alpha I and test some hypothesis about alpha I. In the fixed effect model, the conclusions about the test hypothesis regarding alpha I will apply only to the K treatments considered in the experiment. These conclusions cannot be extended to the other remaining treatments which were not considered in the experiment. In case of random effect model, what happened? We have considered a large number of classes or treatments and we want to test if all these class effects are equal or not. But due to time, money or administrative convenience, it may not be possible to include all the classes or treatments in the same experiment. In such a situation, we take only a random sample of treatments in the experiment and after studying and analyzing the sample data, we want to draw conclusions which should be valid for all the classes, whether included in the sample or not. In such a situation, the parameters alpha i's in the model will not be fixed constant but will be random samples and consequently the model is termed as random effect model. In the random effect model, if the null hypothesis of the homogeneity of treatment effects is rejected, then to test the significance between the two treatment effects, t-test cannot be applied as all the treatments are not included in the experiment. So dear students, I conclude today's lecture here. Thank you.